future directions or potential collaborations. So that's the purpose of this from my perspective. So this work is mainly done by my PhD student. So he's graduating in a couple of months. So anyone looking for a postdoc, he's available. And so the idea is to introduce a methodology to find ACC-driven vehicles in a vehicle trajectory data. So vehicle trajectory data has been around for a while. I mean, probably more than 50 years we have some data collected, but reality of this, the very first meaningful trajectory data set that was used extensively was the NG-SIM. But since then, the applications of trajectory data has been expanded. So initially intended to do driver behavior, now people are doing a lot of traffic analysis. There are companies that are collecting trajectory data just to do traffic analysis, replacing what we used to do with loop detectors. Collision analysis has been adopted this approach for a while, and then AV research has been all about vehicle trajectory and trajectory prediction of surrounding vehicles, in the AV sensor range, and so all of these are really based on this type of data, and this provides an opportunity to be able to combine multiple of these fields into, bring them under one umbrella to do a very comprehensive convergence research. So our motivation was, so there's been a lot of data sets out there, at different types. So like in Sharp2, you may or may not call the trajectory data. NG-SIM I mentioned. So there's TrafficNet, there's HIDI, which is very accurate data collected in Germany using drones. And so I'm going to introduce you a new data set that we collected in Austin, and then we're also doing a project sponsored by Federal Highway, collecting data in Chicago, trajectory data in Chicago, in Washington, D.C., and that is an extensive trajectory data set going to have over 10 hours of trajectory data collected on highways. So, and there's one issue with all these existing data sets, however, and that is as new technologies find their way into the transportation system, we don't have any meaningful way to characterize the vehicles based on those technologies. So if you have an ACC-driven vehicles, an ACC-driven vehicle on the road, so its behavior is supposedly to be different than what human drivers supposed to behave, and we don't have a very accurate way to say, hey, this is an ACC and this is a human-driven vehicle, and that matters for many reasons. Particularly, there are several studies, including one of ours, and several really interesting studies by Jorge that show that ACC behavior can be very different than what human drivers can, and consequently it might have different impact on the traffic flow dynamics and how we are going to create congestion management strategies. So it's going to impact a lot of things, and especially as these technologies, market penetration of these technologies increases a lot. So, and almost any car you can buy today, that's any car over $15,000-$20,000, will have some sort of adaptive cruise control on it as by default. So these things are becoming widespread and common technology among cars, and we really need to find a way to identify them when we're collecting data. So the challenge again was there's no trajectory data that really that has ground truths for this purpose. So I could get HIDI data set. I'm pretty sure there are vehicles with adaptive cruise control in that data set, but there's no ground truths for comparison. And so for that reason, we decided to collect our own data. So we collected the data on I-35. We had 3 vehicles with full rate adaptive cruise control, and we had over 2 hours. We had 5 runs of these vehicles and going through. So these vehicles formed a platoon of ACC following each other, and then they just went through this, and we had an aerial videography to collect the data from that segment. So, and as you can see, the dynamics of these 5 runs. Well, 5 runs is really not enough, but and I'll get to what needs to be done to increase this and what we're doing here in Chicago. But over 2 hours, we could only, because of congestion, we could only do 2 rounds. Like you had to go through the whole loop, and that took us took us so long that we could only finish 5 runs in 2 hours, and each run takes about like 1 to 2 minutes. So, but the dynamics of even these 5 runs are very different. So, in one of these runs, so these are the 3 good ones. The other 2, in one of them, actually, someone cuts between the last vehicle and the second vehicle, and then in another one, the platoon actually completely, for a short period of time, completely was the warfare dismantled. So maybe so. So they lose connections. They're no longer a platoon. It's still moving at ACC, but they were able to form a platoon over again. So for meaningful analysis, you really need more than 5 runs. I totally understand that. So this is considered this study as some sort of proof of concept that what you're proposing might actually work well if you have a larger, better data set. So this was a process of collecting, extracting trajectories. We had the vehicle detection, which and then we had also the tracking and making sure the vehicle IDs are the same. And then once the vehicle IDs are the same, then we could actually match every frame to a reference image, so know exactly where each pixel is in XY coordinate, and then create the trajectory. So the trajectories are a lot shorter. So this is about 400 feet, obviously. So, and then, but the smoothness of the trajectories are not really comparable to what we see at NGSIM. That is amazingly more robust and more reliable than, and the technology has changed over 15 years. And this was collected in 2019, so over 14 years. So, but this is like this is a trajectory data set for for each lane. So this is, you see like some very nice shock waves on the 2 left lanes. So, and the right lanes, the 2 right lanes on the right side had not much shock wave despite being a very congested roadway. So, what are the objectives again? We want to introduce a robust methodology to identify vehicles with ACC, or at least vehicles that drive just like ACC. So maybe I can argue that there might be some humans that can drive just like ACC in a short period of time. And then investigate the difference in behavior of conventional vehicles, human-driven vehicles, and ACC, and see how do they really show up in terms of flow density relationships. So our approach was based on clustering. So we can have probably many different approaches, but clustering in any sort of unsupervised learning approach would be a very reasonable approach for us, because we had some ground truth. So at any instance, we had 3 ACC-driven cars, and we wanted to see if we can find other ones similar to their behavior. So clustering would be a natural first choice, because it could tell us whoever is put in the same cluster as these ACC vehicles should have a behavior close enough to these ACC-driven vehicles, so we can categorize it as ACC. So each run was investigated separately because the traffic condition changes between the runs. So combining one versus the other wouldn't result in a very good outcome. And I have some discussion on that and what can be done to make this more generalizable. But we use, and this is like the plots of the ACC vehicles and the 3 vehicles following them. And you can see the behavior is actually drastically different in some cases, and in some cases not as much. So the one like all the way like 3 vehicles behind has its own really trajectory, has nothing to do with the ACC-driven cars. The one right behind them has some similarities, but still you can distinguish the behavior that this is not really ACC, and I'll get to that in a minute. So we picked essentially 4 features and their changes: the speed, acceleration, time headway, space headway, and their changes over time. So, and these were the features for clustering. But we can't really look at one single instance in the clustering process and say, okay, this instance, because of this behavior, it's ACC, and this instance is not. I'm not saying we can't, but it's going to be a super complicated process. So we need to capture the whole trajectory and compare the trajectories rather than just a single vehicle, or at least a good portion, so we can see the continuation of the behavior. We had to do normalization of the obviously normalization of the features because the scale of them are different, so speeds are much larger than acceleration values. So in that case, speed would be the dominant feature, so we didn't want to do that, so we normalize everything. And we use PCA to construct uncorrelated features. So rather than just using these, we wanted to make sure that whatever we pick would be an uncorrelated feature. So PCA works based on essentially the principles of SVD in linear algebra, if you're familiar with it. So the distance measure between the trajectories, so I talked about it. We don't want to use a single point, so we want to use a trajectory or maybe parts of a trajectory to do the clustering. So we need to define the distance between the trajectories. So Euclidean distance is not going to work well because when you have 2x3s with multiple data points, using Euclidean distance between them would be quite complicated, particularly because the two trajectories might not have the same number of data points. So there are solutions to this. So there are two key solutions to this. One is warping distances. So dynamic time warping is a very common approach, a very good example of this. So it tries to match the points in one time series data to as many as it can in the other. So that way you don't have an issue with the duration of the time series or the shape of it. So essentially it just compares the shape of them. This has been widely used for animal sound detection. So if you have like some sort of, I don't know, like a bird or a fish, dolphin, and you want to see if what you hear now, if you can categorize its species based on your data set, dynamic time warping has been used extensively for that. Just try to match that new sound that you recorded to the existing data set of the animal voices, so that way you can find it. So there's also another one, longest common subsequent, LCSS, which is another thing, in the warping distance. We also use shape-based distances. So I can't really pronounce it. I'm not sure. I'll butcher the name, but Fractured and Hansdorff. But these are looking at the similarity in the geometry of the two trajectories. So it looks at how similar they are from the geometric perspective, not just trying to match the points together. So, but both of these approaches would kind of like get rid of the challenge of the inconsistent or different trajectory durations. So we use two clustering approaches. So you can pick anything. So we particularly pick these two for two particular reasons. So hierarchical clustering, you don't need to prefix the number of clusters, so you can adjust it, which is very useful. So here, for instance, you can have two clusters. This whole thing is one, and this one is one. Or you can have, you can have three. In that case, this one would be one, and this one would be another one, and maybe four, and this one would be another one. That case, so you can adjust the clusters based on what you want. The other one, or based on what you think would be meaningful division. The other one is affinity propagation, which automatically determines the number of clusters. I particularly like affinity propagation because it requires some sort of a back and forth communications between data points. So the data points pick if they want to be a cluster head or not, and also they pick who they want to connect to. So this way, over a process of going back and forth between the points, you can actually put them in the clusters that would make most sense. So affinity propagation is a very interesting approach to cluster without the need to deal with the number of clusters or picking cluster heads or cluster centers or anything like that. So any questions so far? Okay. So we implemented these, and
Hello, sorry. Yeah,
Yeah,
sorry, I do have a question. It's just that I couldn't unmute myself quickly enough. Yeah, and the shape-based distance, you were analyzing like distance, di- I mean, distance difference between lead and followers, like ACC and conventional vehicles, or just ACC, or
no,
what?
so okay, so this is a great question. So for all of them, we essentially have a pool of trajectories in within our data set, right? So what we're going to do is we're going to put our ACC cars in that pool and cluster the whole thing, and then we're going to see where those three ACC cars are going to fit in, and we're going to see if that makes all other cars within that cluster to have the similar behavior. So regardless of the distance metric that you use, that's the overall approach. So not just a follower or leader or anyone, we're going to include everything that we see essentially.
Oh, okay, got it. Thank you.
So yeah, the idea is to find if there are any other ACC-driven cars on the road. And from traffic flow analysis, this is valuable, but also from autonomous vehicle perspective, because predicting the trajectory of other cars around is a key element of motion planning for them. So the motion planning algorithms rely on accurate prediction of how vehicles move around. So knowing if someone is driving based on ACC or versus the human, that can significantly change the accuracy and improve the accuracy of prediction. So it has values on both ends of just not just traffic. So all good. Okay, great. So essentially what we did was we um, put everything in one pool. So for each run, so number of vehicles that we see around the same period of time that the ACC vehicles were crossing this section. So we took the trajectories of all of those cars and see we started to clustering them, and we used different distances. So this is the number of clusters that we observed in each run. You see, like the geometric shape-based approaches didn't perform well. So for instance, in run two, uh, every single ACC ends up in a different cluster. So we have three ACC cars, each ended up in a different cluster. So that's not a good thing. So we know it's not capturing the behavior of ACC, because if the ones that you have and you know they are ACC are not in the same cluster, you know that's not really capturing the similarity in the behavior. So overall, the dynamic time warping performed the best. So this is the runs that we saw. So the first three runs were the ones that I showed you. The fourth one was the one that we had one vehicle caught in front between the last and the second vehicle. So essentially, what happened was the behavior of the last vehicle had to change because we had to take over. So that vehicle ends up in a different cluster. So the other two was in the same cluster. The first two vehicles were in the same cluster. The last two was essentially became a human-driven vehicle because we had to take over. And so that two clusters here, and then again one cluster in the last one. So dynamic time warping performed pretty well on our ground truth data set. Uh, so some of them are also do fairly well. So LCCS, you can tune these up if you spend enough time to get a very good result. But we didn't see a point in doing that because dynamic time warping was already performing as we expected, as we are hoping. So not expected really, as we're hoping. So every other analysis that I'm going to present to you is essentially based on dynamic time warping. So as I said, each run was investigated separately because the traffic behavior between run 5 and run 1, so there's like roughly 1.5 hours between the two, changed significantly. So this one, run 1 was not as congested, run 5 was fairly congested. So, and we only look at the congested location. I'll talk about that in a minute more. So these are the statistics of time headways and space headway for different clusters. So you can see like for instance this is a cluster of the ACC vehicles. So, and you can follow the behavior of them. So the value of doing this was for us to kind of like try to better understand if we can see distinct behavior. We did this not just for time and space headway, we did this for all the measures that we did and we used. So every result that we captured, we investigated essentially everything by hand to make sure that whatever we see there is meaningful and there's a distinct difference. So we performed a lot of statistical tests, and we made sure that the outcome of what we are trying to do is statistically significant. So, and so I'm not going to go through the details of the tests that we did, but we did quite a bit of tests on the variance and the mean and distribution of the headways and distribution of headway between the clusters in each run. So we want to make sure that whatever the clustering outputs is meaningful. It's not just an artifact of the clustering, but also there's a meaningful distinction between the clusters. So once we have the clusters, now we wanted to do, so each cluster had, if we use dynamic time warping, each cluster had 3 ACC vehicles, except the fourth one, which let's say we threw it away for now. And each cluster has 3 ACC vehicles and a whole bunch of other cars. And if you look at here, like for instance, this is the cluster of essentially ACC vehicles, and cluster number 5, which had roughly about 16 cars in it. So they were like, within that time frame of a few minutes, we identified an additional 13 vehicles that had same behavior, similar behavior to ACC-driven vehicles in run 5, for instance. Or if you want to go here, so this one, the same 16. So in this one, this was a 15 vehicles. So in this one, the cluster here, we only had like 7 or 8. So the number of ACC-driven vehicles in each run were different, and which makes sense because you don't always have the same number, obviously. So what we did was we took every cluster that we had and we calculated the speed flow diagram and flow density speed flow diagram for them, and to see if we aggregate them, there's a meaningful difference between them. So we see, like, from the disaggregate perspective, from the headway, from the speed, all of them were statistically different, but we want to see how does the behavior look like when we plot them separately. So some clusters ended up being very distinct. So for instance, here the cluster number 4, these green stars are ACC-driven vehicles. They cluster with ACC-driven vehicles, and it's very distinct than the rest. Here the same, so they have much higher speed and also similar flow, but they're very distinguishable between them. So some runs, they were not as distinguishable, or at least not in the aggregate measure. So if you look at, like, run 4 is essentially very different. So we said we're going to throw it away pretty much. But run 5, they're not very distinguishable. So they're mixed with everything else. The same for run 3. So the level of confidence that they had in these two was much lower than this. And the statistical tests also showed that pretty well. So run 1 and run 2 were a lot more distinguishable than the other ones. So, but this is like comparing those graphs to the aggregate if you just plot the whole thing. So system was, well, obviously we're on the congested side of this system, but really everything is pretty smooth, not much scatter in front of the diagram. You can, in the speed flow diagram. But when you plot them separately, you can see, at least in some of these cases, you can see a distinct difference between how ACCs are going to shape the system versus the other human-driven vehicles. So if I want to sum this up, we tried to address a challenge in the existing trajectory. So by introducing a new data set and proposing a potential approach to detect ACC-driven vehicles in the system. So since the ACC-driven vehicles are not labeled, and so we wanted to use we decided to use an unsupervised learning to find which direction is the right way to go. Well, the clustering results with different distance measures indicated that dynamic time warping is probably the best approach to do this, and there's a very good reason for that. And if you look at the way that dynamic time warping shapes the distance between the trajectories, it does it in a stepwise manner. So it picks the first trajectory, goes to the second one, tries to match as many points as it can to the first one. So it kind of like at the same time conserves the time stamp of the trajectories, which is really nice. And then so statistical analysis indicated that there's difference between the behavior in these dynamics in these clusters, but we also found that round one and round two things are a lot more distinct than the other three. And so there's a lot more things to do here, but this is what look at this brings as some sort of proof of concept for this process. Okay, so and if you have any questions, I'll be here for a while. So no, I don't have my picture. Yeah, it's okay. Okay, so yeah, any questions?
Okay, thank you. Thank you, Dr. Alireza. It's very not short, but very nice, very interesting presentation. Okay, the audience, please feel free to unmute yourself to ask questions or leave it in chat box.
Oh, there's a chat box? I'm sure.
Yes, I can monitor that for you.
Oh, there it is. I found it. Okay.
Hi, Alireza. This is Jorge. I have a question for you.
Yeah, go ahead.
Yeah, so it looks like a trend for these autonomous vehicles is going to be imitation learning, so imitate the human. So in that context, this method will face even more challenges, right?
Yeah, I mean, at some point it's going to be useless, absolutely. If they start imitating humans, absolutely it would be useless. So, this part of the reason we focused on ACC was this. So I know there's some companies that do, like for instance, RL-based autonomous driving, and one of them I'm going to actually just rate like $1 billion or something.
Yeah.
And there's some other ones that are using more of a traditional robotic space, right? And some of them they claim that they're using a combination of them. But I agree. So they're trying to be human-like to avoid like being rear-ended at stop signs and that kind of stuff. So yeah, their behavior is going to be as close as possible to this. I'm not 100% sure how the ACC trend is going really. So, but the current existing ACC system is nothing like human for sure. And so maybe you can say at least not most of them. So maybe yeah, so maybe some of them do, but some of them not. But I totally agree with you. So if they start really looking into imitating humans
Right.
at best, this is going to be absolutely useless. And then there's no point in detecting them in a different way either in that case. So because if everyone is driving similar to humans, why would I want to distinguish them anyway?
Yeah. But so the method would be more applicable to ACCs, right?
Yeah,
Then,
we focus mostly
yeah.
on ACCs because especially the ones that I have seen, they are
Right.
they're fairly robotic, so really reactive systems rather than being really.
Right. So that was my follow-up question. What are the main differences between the ACCs and the human in intuitive terms?
Oh, so the few things we noticed was so their response are very well timed. So the reaction time is pretty much it has a very narrow distribution. So that is a key feature. And so I can't comment about everything else. So none of these things are pretty much none of them are string stable. So the part of the reason for that is they're reacting excessively compared to a situation compared to human drivers. So we always kind of like let it we
Right.
wait a little bit and let's see how it shapes, right? But they always try to be very reactive. So that's what I noticed, but I can't really comment on these things are really changing fast, but these were the two main
Yeah.
things that we found overall.
Okay. Very interesting. Thank you.
Yeah, hi, Dr. Alireza. Thanks for the presentation. I just have like a question. Um, so you collected the data like on free flow condition or
No, this was a pretty much fully congested, well, not fully congested, but more of a stop and go. So if you look at the trajectories,
Yeah, I saw a couple of shockwaves in there, but
yeah, so it's like more of a slow and go stop. Some of them like really stop and go, but some of them are not. Like some lanes were free flow. So just actually great point. So just also adding something to what Jorge just asked. So if you have like free flow and everyone is going really at free flow, you can't really distinguish anything from each other. So I know like ACC are supposed to be very consistent, but the accuracy of detection based on the camera is not that great. So we can't really see like 0.5 miles change in the speed really that well. Um, so yeah, so if you have like free flow or ACC versus just traditional cruise in a free flow, you can't really distinguish any of them. So, and again, so there's no point in distinguishing them because they're all going to behave the same way. So why would you want to change anything anyway?
yeah, it's just that, for example, I saw like, a couple of, I mean, there's only like a shockwave in there and not too many. So I was wondering if there was
Yeah,
like
like this is like 300 seconds. You see,
oh,
like this is not the whole thing. This is like 300 seconds.
oh, okay.
So this is happening like literally a shockwave is happening every 300 seconds. So that's like the frequency of this. So that's what I call like more of a stop and go traffic.
Okay. Thank you.
So every 5 minutes you see a shockwave. So, and this is like the first part. So it gets further down, it gets more and more congested. But plotting those trajectories would be meaningless and not look good because it will have like something like this for a long time. So
Is the data available?
the data is available, yes.
Okay, great. Can you maybe put a link?
Yeah, so I'll send it to the organizers and they can share
Yeah,
it. Yeah.
that'd be great. Thank you. We have a question in the chat by Irene.
Oh, okay, yeah. Thanks, Irene. Oh yeah, so we did this in a probably the dumbest possible way. So we calculated the average headway and did like 1/average headway for the flow rate.
Yeah, so the question is how to calculate the flow?
Yeah,
For
how to calculate the flow rate for each cluster of vehicles.
Okay.
So we just took the average headway for that cluster, which is not really the best way to do this, but we couldn't think of anything else.
Hi, Dr. Alireza. I have a question. I noticed that we have 5 rounds and maybe they are congested on different levels. Do you happen to observe some differences of those ACC behaviors when they have different levels of congestion? I mean,
Yeah,
if
so
the speed is below or higher than certain speeds.
absolutely. So the reaction of the ACC changes based on the speed. So at lower speeds, you're not as reactive compared. Like if you're driving at 40 miles versus 10, the behavior of ACC completely changes. So they are a lot more forgiving at 10 compared to 40. And so they're designed to not crash at all costs. So that's why they're reacting almost always overreacting to the situation. So, and do not consider anything around, so just a vehicle ahead. So that's one of the two main challenges. Yeah, but they're different. So if I want to cluster run 1 and run 2 together, there's a good chance that they won't end up in the same clusters.
Okay, I see. So the major change would be the reaction time and maybe the accelerations they use.
Right. So if you
Braking.
have like, for instance, if you have a stop and go versus just a slow moving. So when you have a stop and go, the vehicle takes a long time to speed up and reach the designer speed. But when you from 0, but when you're going at like 5, going from 5 to 10, going from 5 to 15 takes a lot less time than going from 0 to 10. So the behavior is really different, and I still don't know why they designed that way, but I'm guessing. And these are particular type of vehicles that we use. So you might, if you want to pick like, I don't know, Chevy versus BMW, they might have a completely different one. So both of the cars that we drive now, and my wife and I, they have the same issue. So they're different.
I guess that's common That's also how many other people feel when the ACC vehicles start from the full stop. It's usually taking significantly longer than human drivers.
Yeah, that's true.
Yeah, that's a common feature.
Yeah.
But I do agree in stop and go waves and maybe low speed, the behaviors would be very different due to some other safety design. And from the design perspective, they should also be different, I guess.
Absolutely.
Okay. Any other questions? I don't see that in chat box. Okay. Thank you again, Dr. Alireza. That's very interesting presentation, and we're looking forward to see the papers and the data coming up that will benefit the community, I guess.
Yes, I'll send you the link to the data so you can share with the whole community. So
sure. We'll also upload this video to YouTube.
Okay.
And more people can see it. Okay. Thank you, everyone. Thank you for coming. Hope you all have a nice weekend.
Thank you, Hal. Thank you, Alireza.
Thank you.
Thank you, Alireza. Great talk.
Hi, Danju.
Bye.
Thank you.
Bye-bye.
Thank you, guys. Thank you.